An automotive engineer receives 4 communication requirements. A mirror switch must send a simple position request to a small motor controller. A brake status value must reach several electronic control units reliably. 2 chassis controllers need tightly coordinated communication. A camera must send a large stream of image data to a central computer. Should the engineer simply select the fastest network for all 4 jobs? No. Vehicle network selection is not a race to the highest data rate. The correct technology must match the function's bandwidth, timing, cost, topology, reliability, power, and implementation requirements. This is why one vehicle may contain CAN, LIN, FlexRay, and Automotive Ethernet at the same time. Begin with Local Interconnect Network, or LIN. LIN is designed for cost-sensitive local communication where high bandwidth is unnecessary. A small group of devices forms a local subnetwork. One coordinating node initiates communication according to a schedule, and the other nodes provide or receive information when the relevant frame is requested. LIN commonly uses a single communication wire in addition to the electrical reference. Its standard operating data rate is limited to 20 kilobits per second. That is slow compared with the other technologies in this lesson, but speed is not the primary goal. The goal is simple, predictable, and economical communication for devices such as mirrors, seat mechanisms, door modules, rain sensors, climate control flaps, and similar comfort functions. Imagine a mirror switch connected to a door ECU. The door ECU coordinates a small LIN subnetwork containing the mirror motor controller. The switch request does not require camera-level bandwidth. A scheduled, low-cost link is sufficient. LIN would be a poor choice for transmitting video or large amounts of rapidly changing sensor data. It is selected because it satisfies a modest requirement economically, not because it is technically superior to every alternative. Now consider Controller Area Network, or CAN. CAN is widely used for distributed communication between vehicle ECUs. Multiple nodes share a bus, and more than one node can attempt to begin transmission. When transmissions begin at the same time, CAN uses non-destructive priority arbitration. The frame with the higher configured priority continues, while the other node stops transmitting and tries again later. The winning frame is not destroyed by the arbitration process. For classical CAN and CAN-FD, the frame identifier participates in this priority decision. A lower numerical identifier normally represents higher bus access priority. The identifier should not be understood as a simple destination address. It identifies communication content and contributes to arbitration. Classical CAN carries up to 8 data bytes in one frame and is traditionally associated with bit rates up to 1 megabit per second. CAN-FD extends the payload to as many as 64 data bytes and can use a faster bit rate during the data portion of the frame. CAN combines flexible event-driven communication with strong error detection and fault containment mechanisms. Therefore, it is used across body, powertrain, chassis, and diagnostic applications. For example, one ECU can transmit brake pedal status, and several configured receivers can use it. The powertrain controller may use it in torque logic, the instrument cluster may use it as an indication, and a start-stop controller may use it as one operating condition. CAN is not automatically deterministic merely because high-priority frames win arbitration. Engineers still need to analyze network load, frame priorities, transmission periods, blocking time, and worst-case latency. A lower priority frame may wait longer when the bus is heavily loaded. CAN-FD increases useful payload and data phase performance, but it does not remove the need for network design. Next is FlexRay. FlexRay was created for communication that requires higher bandwidth, predictable timing, and optional communication redundancy. A FlexRay channel can operate at up to 10 megabits per second, and the system can use 2 channels. The 2 channels may carry redundant information for fault tolerance, or they may carry different information to increase available capacity, depending on the architecture. FlexRay communication is organized into repeating communication cycles. A static segment provides predefined time slots, allowing important messages to be transmitted at known positions in the cycle. A dynamic segment can support more flexible event-related communication. This time-based organization makes FlexRay suitable for systems that require tightly controlled communication timing. Examples historically include coordinated chassis, steering, and braking functions. The benefits come with additional design and integration complexity, communication schedules, time synchronization, network configuration, and network architecture must be engineered carefully. FlexRay, therefore, is not a universal replacement for CAN. It addresses a different set of requirements. The fourth technology is Automotive Ethernet. Ethernet is not one fixed data rate or one single automotive cable. It is a family of communication technologies sharing Ethernet principles and supporting several physical layer options. Automotive single-pair Ethernet includes technologies operating at 10 megabits, 100 megabits, 1 gigabit, and multiple gigabits per second. For 100 megabit and higher automotive Ethernet links, communication is commonly point-to-point and full duplex. Each ECU connects through a physical layer device to an Ethernet switch or directly to another node. 10BASE-T1S also supports shared medium, multi-drop arrangements for lower-rate Ethernet applications, so automotive Ethernet should not always be drawn as only one topology. Ethernet's scalable bandwidth makes it valuable for cameras, radar data, infotainment, central computers, diagnostics, software updates, and high-capacity vehicle backbone. A camera can produce far more data than a simple door status signal. Instead of forcing that stream through a low-rate body network, the camera can send Ethernet frames through a switched link to a central processing ECU. Ethernet and Internet Protocol are not the same thing. Ethernet defines lower communication functions, while IP can operate above Ethernet. Some automotive Ethernet traffic uses IP-based protocols, but Ethernet does not automatically mean that every vehicle message is an IP packet. Another common misconception is that Ethernet is automatically non-deterministic and therefore unsuitable for time-sensitive communication. Standard switched Ethernet alone does not guarantee every automotive timing requirement, but time-sensitive networking adds mechanisms for bounded latency, traffic scheduling, synchronization, and controlled resource use. The network still requires careful configuration. High bandwidth does not remove congestion, queuing, timing, or security concerns. Return to the original 4 requirements. The mirror control subnetwork can use LIN because the data volume is small and cost matters. Brake status and many distributed control values can use CAN or CAN-FD because several ECUs need robust priority-based communication. A system that requires a tightly scheduled, redundant communication cycle may use FlexRay when that technology is part of the vehicle platform. The camera stream can use Automotive Ethernet because it requires much more bandwidth and benefits from switched communication. These networks can coexist. A door ECU may receive a mirror command through LIN and provide door information to the rest of the vehicle through CAN. A central gateway can connect the CAN domain to an Ethernet backbone. The gateway routes selected information between networks without changing its intended application meaning. The network choice also affects hardware and software. Each technology needs an appropriate controller or communication peripheral, physical layer transceiver, wiring topology, connectors, configuration, diagnostics, and test strategy. AUTOSAR supports this diversity through bus-specific communication paths. An application works with meaningful vehicle information, while lower software handles packing, routing, and technology-specific communication. The upper application meaning can remain driver door status or vehicle speed, even if the lower transmission technology changes. The network frame and software path beneath that value will be different.
If an interviewer asks which automotive network is best, the correct response is not simply CAN or Ethernet. Explain that the decision depends on bandwidth, maximum latency, determinism, cost, node count, topology, fault tolerance, power management, existing vehicle architecture, and software support. LIN is economical for low-rate local devices. CAN and CAN-FD provide robust shared bus communication with priority arbitration. FlexRay provides scheduled, deterministic communication with optional dual-channel redundancy. Automotive Ethernet provides scalable high bandwidth and switched connectivity with time-sensitive networking available for bounded latency use cases. Subscribe to continue building these fundamentals into a complete understanding of automotive software and AUTOSAR architecture. Knowing which network carries the information is only part of the design. The next lesson explains real-time systems and why both software execution and
communication must complete before their deadlines.